Imagine for a second that you are sitting on your couch, just looking at your smartphone. You open up your app store, you see one of your favorite apps has an update, and you just tap that little update button.
Right, something we do every day.
Exactly. And you see a circle spin for a few seconds, a progress bar fills up, and boom, the new version is ready. You open the app, you've got new features, it's running smoothly, and you don't really give the process a second thought. It just works, seamlessly in seconds.
Which is actually wild when you think about what's going on behind the scenes.
Right, because behind the curtain of that seamless experience you just had on your couch, there is an incredibly massive and honestly, historically deeply chaotic engine room.
Oh, absolutely.
Yeah.
It really is an industrial engine room. And for the last few decades, it has been running dangerously hot. We're talking about an environment historically filled with, well, proverbial smoke, sparking wires, and engineers running around with fire extinguishers at 3 in the morning just trying to keep the digital lights on.
Yeah, we have come to expect absolute perfection on the front end of our software. But the back end, the actual mechanics of how software is built, tested, and deployed, has been a high-stress, highly fragmented world. So today's mission is to explore how that exact engine room is being entirely rebuilt from the bedrock up.
It's a total tear down and rebuild.
It really is. We are doing a deep dive into a comprehensive presentation framework by Roman Varel, and it's titled Building the Foundation for NoOps. Our goal today is to trace the evolution of software development from what is basically a tangled mess of overlapping tools into a highly structured automated conduit. They call it the golden pipeline.
The golden pipeline. Yeah, and ultimately we're going to explore where this entire industry is heading, which is a fully autonomous AI-driven future called NoOps.
No operations. It sounds like science fiction.
It does. But we are looking at the true industrialization of software delivery. The industry is moving away from this artisanal, highly decentralized process where, every engineering team builds their own distinct assembly line. And they're moving toward a streamlined, hyper-efficient factory model.
Right. But instead of physical goods, we are manufacturing digital experiences. And this transition requires a complete overhaul of not just the technology, but the human culture that actually creates it. So whether you are managing a tech team and feeling the pain of scaling, or you're curious about how artificial intelligence is moving beyond just chatbots to actually run complex infrastructure, or even if you just want to understand the modern mechanics of why the internet stays online, this deep dive is going to give you a definitive roadmap.
It's basically the blueprint for the next decade of tech.
Exactly. Okay, let's unpack this. We have to start by establishing the baseline of the current chaos, right? Because you can't appreciate the AI future without understanding the deeply flawed human systems we are trying to fix today.
Yeah, that baseline requires looking at a multi-decade pendulum swing. We are currently transitioning out of an era where developers were granted almost infinite decentralized freedom in how they worked.
Freedom sounds good though, right?
Well, yeah, the intentions behind that freedom were good. It was all aimed at increasing speed and innovation. But the ultimate result was massive cognitive overload, burnout, and incredibly fragile systems. So to fix it, the industry is pivoting toward a concept called platform engineering.
Platform engineering.
Right. And that operates on the premise of providing a heavily standardized, robust launchpad for development. And the long-term objective of that launchpad is to allow AI agents to step in and absorb the operational heavy lifting.
Right. But before we get to the AI agents taking over, we really need to walk through a brief history of how we got to this state of gridlock in the first place. If we rewind the clock to the pre-2000s, the source material labels this era siloed IT.
Oh yeah, the dark ages.
Right. This was defined by rigid, almost impenetrable barriers between different departments. You had developers writing the code on one side of the building and operations teams managing the physical servers on the other.
And they basically didn't talk to each other. The culture of that era was entirely transactional and heavily bottlenecked. The phrase constantly used to describe the workflow back then was throwing it over the wall.
Throwing it over the wall.
Yeah. A development team would spend 6 to 9 months writing a massive monolithic block of code. They would finish their part, essentially wash their hands of the product, and toss this massive software package over a metaphorical brick wall to the operations team.
Just here you go, your problem now.
Exactly. Leaving them to figure out how to configure the physical hardware to actually make it run.
Man, the friction there must have been unbelievable. I mean, the operations team is receiving a complex, poorly documented package that they didn't write, and they have to manually install it on physical servers in some freezing cold data center.
And it was a continuous cycle of highly stressful, high-risk deployments. Because these applications were monolithic, meaning all the features, the database connections, the user interface, were bundled into one giant executable file.
Right, all in one basket.
Exactly. So if a single line of code for a minor feature broke, it literally took the entire system offline.
Wow.
And because the provisioning of servers and the deployment of code were entirely manual processes involving physical hardware, releases didn't happen continuously.
Mm.
You saw software updates maybe once a quarter, or twice a year if you were lucky.
That's so slow by today's standards.
It was a slow, agonizing process where the final deployment weekend was essentially a company-wide crisis event, everyone ordering pizzas, sleeping under desks.
Right, the classic 48-hour deployment marathon. But the industry obviously couldn't sustain that model as the internet scaled up. Consumer demand for new features was accelerating, and, well, you can't survive in a modern market if it takes you 6 months to push a tiny bug fix.
No, you'd go out of business.
Exactly. So this brings us into the 2010s, which the text calls the era of grassroots DevOps. This is where the agile movement really takes over, and the entire philosophy shifts towards smashing that wall between developers and operations.
Yeah, DevOps. And that grassroots DevOps movement fundamentally altered the physics of software delivery. Instead of those massive multi-month releases, the industry adopted CI/CD.
Continuous integration and continuous deployment.
Right. Teams started breaking their code down into smaller microservices and releasing tiny incremental changes constantly. Rather than one massive update every 6 months, they were pushing dozens of microscopic updates every single week, sometimes every single day.
And the source material pulls in data from the Doris State of DevOps report to quantify this shift, and I gotta say the contrast is stark. We've known for a while that DevOps creates a performance gap, but looking at the actual multiples between what they call low performers and elite performers really contextualizes the sheer operational strain teams were under.
Oh, the numbers are wild. Low performers were still operating like it was 1999, infrequent releases, manual firefighting, and prolonged outages.
Right.
But the statistical gap is what drove the entire industry to abandon that old model. Elite teams, those who fully automated their pipelines and embraced collaborative DevOps, were deploying code 208 times more frequently than low performers.
208 times.
Yeah, but the truly critical metric is the MTTR, the mean time to recovery.
Right, how fast you can fix a mistake.
Exactly. When an elite team deployed a bug that broke the system, their recovery time was 2,604 times faster than a low performer.
Okay, wait. A multiple of over 2,000. That fundamentally changes the risk calculus of running a business. I mean, if a catastrophic failure takes a low-performing team 2 weeks of manual log reading and server restarting to fix, the business loses millions of dollars, right?
Yeah.
Massive customer trust.
Huge losses, yeah.
But an elite team fixes that same catastrophic failure in a matter of minutes. That's the difference between sending a letter via the Pony Express and sending a text message. It completely alters your expectations of speed and reliability.
That's a great analogy. And the mechanism behind that speed is tied directly to the batch size of the works.
What do you mean by batch size?
So if you only deploy one tiny change and the system crashes immediately after that deployment, you know exactly which line of code caused the crash.
Oh, right, because it was the only thing that changed.
Exactly. You just roll back that one tiny change. You don't have to sift through 6 months of accumulated code trying to find the needle in the haystack.
That makes total sense. Now, on paper, this grassroots DevOps era sounds like a solved problem, you know? The walls are gone, everyone is collaborating, deployments are lightning fast, and recovery takes minutes. But the framework explicitly outlines a severe dark side to this revolution.
Yes, it definitely does.
The autonomy that enabled DevOps eventually mutated into something highly destructive, which they call the tool sprawl crisis. Let's get into that.
Yeah, so the vulnerability of the grassroots model was that the decision-making was pushed entirely down to the individual teams. The prevailing philosophy at the time was absolute decentralization. Basically, give every team the freedom to choose whatever bespoke tools they want to get the job done.
Right.
If Team A wants to use Jenkins for continuous integration, let them. If Team B prefers GitLab, great. If Team C wants to monitor their application with Datadog while Team D uses New Relic, that's their choice.
It's the ultimate manifestation of choose-your-own tool culture,
Right.
which, sounds incredibly empowering at the individual developer level. But when you zoom out to the enterprise level, you are left with a fractured, totally unmanageable landscape.
The framework highlights the tool taxes created, and the data paints a very clear picture of gridlock. Over 50% of enterprises report maintaining more than 20 distinct DevOps tools simultaneously.
20 different tools just to ship code.
Yeah. And because of this massive fragmentation, 74% of DevOps teams report lacking end-to-end visibility across their own delivery pipelines.
They can't even see their own work. The text actually pulls a quote directly from the Google site Reliability Engineering Principles to emphasize the cost of this. The quote notes that without a unified tool chain, teams waste countless hours reconciling disconnected logs, metrics, and test results.
Which is soul-crushing work for an engineer.
Exactly. And I think we need to unpack the friction here because for the last decade, the loudest voices in the tech industry have championed developer autonomy. The argument has always been that empowering developers with freedom of choice leads to innovation. So wait, how does giving an engineer the tools they explicitly ask for actually lead to slower time to market, massive cognitive load, and systemic burnout?
It's a paradox, right? But it comes down to the realities of complex systems architecture. When an enterprise allows 20 different tools to manage the pipeline, they are just buying 20 tools. They are taking on the engineering burden of forcing 20 completely different software ecosystems to communicate with each other.
I see.
Developers were no longer spending their days writing business logic or building actual features. They were spending half their week writing custom, brittle scripts just to force a security scanner to talk to a deployment tool. Tools that were, frankly, never designed to integrate in the first place.
So the cognitive load shifts from solving complex software problems to basically solving administrative plumbing problems. It's like giving every construction worker on a skyscraper site the absolute freedom to bring their own preferred brand of bolts, their own distinct measurement systems, some metric, some imperial, and their own blueprints for their specific floor.
That is exactly what it's like.
Right. You might have very happy individual workers, but the building is going to collapse because the plumbing from floor 3 just doesn't connect to the pipes on floor 4.
Individual autonomy at the micro level created total paralysis at the macro level. When something inevitably broke in production, debugging became a massive forensic undertaking. A developer would have to log into 4 different monitoring platforms, export the data into a spreadsheet, manually align the timestamps, and just try to guess what happened.
What a nightmare.
And furthermore, from a financial perspective, the CFO is looking at spiraling redundant license costs. An organization might be paying for 5 different enterprise licenses for tools that all perform the exact same function, simply because different internal factions refuse to compromise.
Right. Team A refuses to give up their favorite tool. Team B refuses to give up theirs. So the grassroots model clearly hit a ceiling. The industry realized that giving everyone a custom hammer and saw resulted in a chaotic, inefficient construction site. They needed a centralized blueprint, which leads us directly into the second section of the framework, the bridge to sanity. This introduces platform engineering.
Platform engineering is the architectural response to the tool sprawl crisis. If grassroots DevOps was about giving everyone a machete to hack their own unique path through the jungle, platform engineering is about the organization taking control, clearing the jungle, and laying down a highly optimized, fully integrated, paved road.
The concept of the paved road is fascinating to me because it implies a choice, but a heavily weighted one. You are telling developers they don't strictly have to use the centralized platform, but the platform is so frictionless, fast, and secure that they would be actively punishing themselves by trying to maintain their own custom trail in the jungle.
Right. Why use the machete when there's a highway?
Exactly. The text draws a side-by-side comparison between the old grassroots autonomy and the new platform engineering model. Let's look at how the daily experience changes for the developer, starting with developer flow.
Under the fragmented model, a developer's flow was defined by intense context switching. To get a single feature deployed, a developer might have to write code in one integrated development environment, their IDE, then switch to a web portal to trigger a build, then log into a third system to review security vulnerabilities, and finally monitor a fourth system to see if the deployment succeeded.
And every single context switch shatters their focus. You lose your train of thought completely.
Exactly. On the paved road, the platform team provides a unified IDE. The framework highlights a strong reliance on VS Code, standardizing the workspace so the developer rarely, if ever, has to leave that single interface. The security alerts, the testing feedback, the deployment status, it all pipes directly back into the environment where they are already typing.
That's huge. And then the comparison moves to visibility and that critical MTTR metric we talked about earlier. The old way required hunting through fractured logs across multiple disjointed platforms, like you said, exporting to spreadsheets.
Right.
But the platform engineering approach establishes a single source of truth. And the text explicitly points to OpenTelemetry as the mechanism to achieve this. By standardizing the instrumentation, every log metric and distributed trace is funneled into one centralized dashboard. Now, we should pause on OpenTelemetry for a second because understanding the mechanics of how it solves this visibility problem is really crucial. It's not just a dashboard, right? It's a standard way of tagging data.
Yeah, it solves the timestamp alignment nightmare. In a microservices architecture, a single user click on a website might trigger requests across 20 different internal services.
Wow, 20 just from one click.
Easily. And if those services are using 20 different logging tools, piecing that user's journey together is almost impossible. OpenTelemetry provides a standardized protocol for generating and collecting traces. It attaches a unique context ID to that initial user click, and that ID is propagated through every single service the request touches.
Like a tracking number on a package?
Exactly like a tracking number. When a developer looks at the central dashboard, they see the exact chronological path of the request, highlighting exactly which specific microservice caused a bottleneck or a failure.
It turns a chaotic scavenger hunt into a clear, linear map. I love that. And of course, the final point of comparison in the framework addresses the financial bloat. The paved road eliminates redundant license overhead. The organization selects the best-in-class tool for each function, negotiates a massive, consolidated enterprise contract, and mandates its use, wiping out the shadow IT budgets practically overnight.
Yeah, the CFOs love that part. But to physically construct this paved road, the framework outlines an architectural model for agile delivery that rests on two massive non-negotiable pillars.
Okay, 2 pillars. What's the first one?
The first pillar is standardization. This is the organizational mandate to define a unified framework, curate a specific set of approved tool sets, and build an internal developer portal. The platform team essentially absorbs all the cognitive load of toolchain maintenance so the application developers can return to just building applications.
So the developer just develops.
Right.
And the second pillar is cloud-native infrastructure. This is where the actual computing power lives, and we have to discuss the paradigm shift in how servers are treated. It's a classic industry concept, but the scale at which it operates now is just staggering. The framework references the transition of infrastructure from pets to cattle.
Ah, yes. It is the foundational metaphor for modern systems architecture, and it perfectly encapsulates the shift in operational psychology.
Let's break that down for the listener. For a long time, physical servers in a data center were treated like pets. A company would buy a massive, expensive machine. The operations team would give it a custom name like, I don't know, Gandalf or something.
Usually Gandalf.
Right, and they would nurture it. If the server experienced a memory leak or a configuration error, an engineer would log into that specific machine, carefully diagnose the issue, apply custom patches, and gently nurse it back to health. The machine was unique, irreplaceable, and highly fragile.
But the cloud-native pillar dictates that infrastructure must be treated like cattle. Servers are no longer physical boxes you name and nurture. They are ephemeral, virtualized compute resources. They are generated with random alphanumeric tags. And crucially, if a piece of this ephemeral infrastructure exhibits anomalous behavior, you do not log in and try to fix it.
You don't try to save it.
No, you instantly destroy it, and the automated system spins up an identical, pristine replacement in a matter of milliseconds.
The mechanics of that are just incredible. And that's what allows modern platforms to survive massive traffic spikes, right? Like if a streaming service releases a massive hit show, the cloud-native infrastructure autonomously breeds thousands of these ephemeral tattle to handle the millions of concurrent viewers. And the moment the viewership drops, it slaughters them to save money.
Exactly. This dynamic scaling is driven by infrastructure as code, where servers are summoned into existence by standardized scripts rather than human clicks.
And both of these pillars, standardization and cloud-native infrastructure, must rest on a foundational base labeled data-centric observability. The architecture mandates that every single event generated by the pipeline streams into a unified data lake. Which makes sense because you can't automate a system if you cannot clearly see the state of the system in real time.
Precisely. This architecture culminates in what the framework calls the golden pipeline. It represents the transition from a messy, chaotic web of overlapping integrations into a streamlined, high-speed rail line for software. It utilizes pre-built templates, embeds security natively, and relies on that centralized data foundation.
But the value of a high-speed rail line depends entirely on the efficiency of the stations along your route, right? If a high-speed train forces passengers to disembark, manually carry their luggage across the station and board a completely different train at every single stop, well, the velocity of the system just drops to zero.
It defeats the whole purpose of the train.
Exactly. Which brings us perfectly into the mechanics of Section 3. The 4 layers and shifting security left. We have the blueprint for the golden pipeline, but how does it physically operate day to day for an engineering team? The core directive of this pipeline is that every layer must integrate seamlessly to completely eliminate manual handoffs.
Right. Because the moment a human engineer has to copy and paste code from one system to another, you introduce friction and the probability of human error.
So the pipeline is divided into 4 chronological layers of automation. Layer 1 is plan and code. Tell me about that.
This encompasses the initial requirement gathering, the standardized IDE workspace we discussed, like VS Code, and version control. Version control is the system that tracks every single keystroke and code alteration made by the development team, allowing them to merge their work without overwriting each other.
Got it. And layer 2 is build and test. So once the human developer pushes their code to the repository, the automated systems take over. This includes continuous integration, where the raw code is compiled into an executable artifact. But more importantly, it includes comprehensive integration and system testing.
And the automation here is absolutely critical. The system spins up a temporary replica of the production environment, deploys the new code into it, and runs thousands of automated test scripts to ensure the new feature doesn't break any existing functionality.
And if it does?
If a test fails, the pipeline immediately halts and alerts the developer. No broken code moves forward.
Assuming the tests pass, we move to layer 3, deploy and run. This utilizes those infrastructure as code scripts to automatically provision the necessary cloud resources, spinning up the required cattle, so to speak.
Right.
And it uses continuous delivery to push the new application state into the live production environment, seamlessly shifting user traffic over to the new version without any downtime.
And finally, layer 4 is measure. The pipeline continuously monitors the health of the live application using platform-agnostic analytics, feeding that telemetry back into the centralized observability platform we talked about earlier.
Okay, so that covers the mechanical left-to-right flow of building and releasing software. But the most transformative aspect of this golden pipeline is how it completely re-engineers the concept of security.
Oh, this is a massive shift.
Yeah. The text notes that in the grassroots era, security was bolted on at the release gate. But the modern platform engineering mandate is to implement shift-left security. Let's dive into the actual mechanics of what shifting left means, because it's a brilliant systemic fix to a massive operational bottleneck.
To visualize shifting left, you have to look at the timeline of the 4 layers we just talked about. Left represents the earliest stages of the process, the developer typing in their IDE. Right represents the final state of the code running live on the internet. Historically, the security audit happened at the extreme right edge of the pipeline. A development team would spend months building an application, and right before the launch date, a separate security team would swoop in and run penetration tests and massive audits.
And they would inevitably find dozens of critical vulnerabilities, right? Slam on the brakes, block the release. It created intense animosity between developers who just wanted to ship their features and security teams whose entire job basically felt like it was to just say no.
Exactly.
It's the equivalent of building an entire automobile on an assembly line, waiting until it's fully painted and sitting on the dealership lot, and only then checking if the brake lines were installed correctly. If they weren't, you have to tear the entire finished vehicle apart.
Which is incredibly expensive and slow. So, shifting left takes those security audits and embeds them organically throughout the early stages of the assembly line. The framework outlines 4 highly specific automated security gates that operate without requiring a separate security team to manually intervene.
The level of automation in these gates is incredible. Let's walk through them. Gate 1 happens at the absolute furthest left point possible, right inside the developer's IDE on their local laptop while they're actively typing. It is called secret push protection. What is the mechanism here?
So a really common vulnerability occurs when a developer is testing a local script and hard codes a live password, an API token, or an AWS access key directly into the text file just to make it work quickly.
We've all done it.
Right. But the catastrophic error happens when they forget to delete that password and accidentally upload or push that code to the centralized corporate repository.
The moment that happens, the company's master database credentials are just sitting in plain text for any malicious actor who gains access to the code base to exploit. It's a nightmare scenario.
It is. So secret push protection utilizes a background process running locally on the laptop that constantly scans the code for high entropy strings and specific credential patterns using complex regular expressions. If it detects something that mathematically resembles a private key or a password, it physically intercepts the get command. It blocks the upload and throws a big error on the developer screen. The credential never leaves the laptop.
That is brilliant. It literally saves you from yourself. Okay, so gate 2 occurs during the pull request. This is the moment a developer submits their finished code to be merged into the main project. The framework specifies that CodeQL static analysis and dependency scanning run automatically at this exact juncture.
And the vital mechanism here is that this scan completes before a human reviewer ever looks at the code. CodeQL performs static application security testing by translating the raw code into a queryable database and searching for known logical flaws, like a pathway that could allow a SQL injection attack.
Okay, and what about the dependency scanning?
Well, simultaneously, the dependency scanner looks at all the open source external libraries the developer imported.
Because modern software is mostly assembled from pre-existing open source building blocks, right? We're not writing everything from scratch.
Exactly. So if a developer imports a popular open source image processing library, and the global security community recently discovered a critical flaw in that specific version of the library, the dependency scanner instantly flags it. It identifies the exact vulnerable package and automatically blocks the code from being merged until the developer updates the library to a patched version.
Wow. Okay, gate 3 happens further down the line during the build and test phase. This is container image scanning.
Right. Once the code and its dependencies are packaged into a deployable container image, the scanner dissects the layers of that image. It doesn't just look at the application code, it inspects the underlying operating system utilities bundled inside the container to ensure nothing is compromised before it reaches the production servers.
Very thorough. And finally, gate 4 acts as the ultimate backstop at the deploy stage. The framework defines this as policy as code enforcing compliance gates automatically. How does a policy act as code? I mean, a policy is usually just a PDF handbook somewhere.
Right, traditionally it is. But policy as code replaces human security analysts with executable logic. Using engines like Open Policy Agent, the organization's security mandates are actually translated into code.
Oh, I see.
For example, a corporate policy might state that no data storage bucket can be deployed unless highly specific encryption algorithms are enabled. When the pipeline attempts to deploy the infrastructure, the policy engine parses the configuration files. If the encryption flags are missing, the deployment is hard rejected.
It just fails.
It just fails. There is no human negotiation, no subjective approval process, and no way to bypass the rule.
By shifting the security checks to the left, you are identifying the missing brake lines while the chassis is still bare metal on the factory floor. You prevent the vulnerabilities from ever compounding, which radically accelerates the overall velocity of the team. But building this highly automated, constantly scanning, constantly deploying golden pipeline generates an enormous byproduct.
Oh, absolutely. It generates an overwhelming, torrential volume of telemetry data.
And this leads us to section 4, the data engine. Because we have thousands of automated tests, security scans, build logs, and infrastructure metrics firing continuously. If you just dump that into a massive database, it's useless noise. How does the framework propose organizing all this?
The framework details an architecture designed to harvest these signals and convert them into strategic business value. And it starts with what it calls the input layer.
And the schematic for this is massive. It lists over 83 native connectors functioning as an intake manifold. They're automatically harvesting DevSecOps signals across every conceivable tool, the Git repositories, the CI runners, the container registries, the cloud providers. It's pulling from everywhere.
And the mechanical advantage of these native connectors, which often use webhooks or background polling mechanisms, is that they operate passively.
Yeah.
No developer is required to manually fill out a status report or update a spreadsheet. The pipeline itself reports its exact status at every millisecond.
That's a dream.
But raw data is just a storage expense unless it is correlated.
Right. The genius of the system is what happens next. All of those raw signals from the input layer flow into a central processing hub labeled Unified Insights. It acts like an automated logistics sorting facility. It takes a chaotic avalanche of raw data packages, normalizes the formatting, aligns the timestamps, and routes them into 4 highly specific, vital business performance categories.
And this is where the initial pain of forcing standardization really pays off. Because every team is using the same IDE, the same pipeline, and the same OpenTelemetry standards, the data naturally aligns. The Unified Insights Engine can instantly calculate 4 critical pillars of performance across a massive enterprise.
Let's examine these 4 pillars because this is what leadership cares about. The first is velocity. This is purely measuring the speed of the machine. It tracks lead time, which is the total chronological hours from the moment a developer commits code to the moment it is running live for users, and deployment frequency.
Then the second pillar is quality, which acts as the counterbalance to velocity. Moving at breakneck speed is useless if you're just deploying broken software faster.
Right, you're just failing faster.
Exactly. The quality dashboard measures the change failure rate, what percentage of our deployments cause a degraded state, and it tracks the MTTR, proving how quickly the automated pipeline can roll back a failure.
The third pillar is risk. This directly leverages the telemetry off those shift-left security gates we just talked about. It measures vulnerability remediation time. So when CodeQL flags a critical flaw, how many days does it take the engineering team to actually patch it? It also tracks compliance drift, constantly scanning the live infrastructure to ensure no one has manually logged in and disabled a security policy behind the scenes.
Which happens more often than you'd think. And the final pillar is cost, providing direct visibility for financial leadership. It correlates the real-time cloud infrastructure spend, identifying if, say, a recent code change accidentally caused a massive spike in server usage, and it verifies the license consolidation, proving that the tool tax is actively being eradicated.
When you look at these 4 pillars, you realize that attempting to gather these specific insights in the old fragmented grassroots model would be a data engineering nightmare.
Oh, completely impossible.
You would need a dedicated team of analysts constantly writing custom scripts to pull CSV files from 20 different APIs, trying to manually scrub and align the data into a fragile dashboard that is, frankly, fundamentally obsolete the moment it renders. The golden pipeline makes this real-time and effortless.
But the dashboards are merely a secondary benefit. The Unified Insights Engine is not just for human managers to look at pretty graphs. Clean, correlated, real-time data is the fundamental prerequisite for the most significant technological leap in the history of the industry.
Which brings us to the core thesis of this entire presentation. Section 5, the AI readiness equation. Everything we have unpacked so far, the painful transition to platform engineering, the standardization of the tools, the complex shift-left security gates, and the massive data engine was entirely laying the groundwork for artificial intelligence.
That's the punchline. The ultimate destination of platform engineering was never simply a more efficient human workforce. The goal has always been to construct an environment where autonomous AI agents can operate safely and effectively.
The text highlights a defining principle here, and I'll quote it. Fragmentation starves AI of the correlated data it needs. Standardization is the foundation that NoOps automation stands upon.
Let's break the mechanics of this down. Why is it impossible to just deploy an advanced generative AI model into the old, messy grassroots tool chain and instruct it to maintain the systems?
It comes down to how large language models and multi-agent systems process information. AI requires immense contextual clarity and consistent patterns to generate reliable outputs. If you deploy an AI agent into a fragmented architecture where the logging format for the front-end team looks completely different from the database team's format, the AI just cannot map cause and effect.
It gets confused.
Highly confused. If the deployment tools and the source code repositories are disconnected, the AI lacks the required context window. It will hallucinate, confidently execute destructive commands, or simply fail to comprehend the state of the system altogether. It's a perfect parallel to the challenges of training a self-driving car. Think about it. If you take a self-driving AI and drop it into a meticulously planned city where every stop sign is a standard red octagon, the lane markers are freshly painted, and the traffic lights follow a strict global protocol, the AI will learn quickly and drive flawlessly.
Right.
But if you drop that exact same AI into a chaotic environment where every neighborhood uses completely different shapes for stop signs, the lane markers change color randomly, and the traffic rules contradict each other, which is exactly what tool sprawl looks like in software the AI cannot function. It crashes. By enforcing the golden pipeline, the organization is systematically repainting the lanes and standardizing the signs so the AI can finally be trusted to take the wheel.
That analogy captures the necessity of the environment perfectly. Roman Varel's framework distills this prerequisite into a literal formula for achieving this future state, and he titles it the AI readiness equation.
The formula outlines 3 specific variables that, when combined, create the launchpad for NoOps. Variable 1 is standardized tooling.
which we covered the mechanics of with the unified IDE and centralized repositories. The framework notes that standardized tooling enables an AI agent to generate code, write unit tests, and diagnose logic errors within a highly predictable context. If the AI understands the rigid boundaries of the workspace, its generated code will actually compile and function.
Variable 2 is cloud-native infrastructure.
This relies entirely on the concept of ephemeral cattle and infrastructure as code. Think about it. An AI agent does not possess physical hands, right? It cannot walk into a data center and swap out a faulty hard drive.
Not yet, anyway.
Right, not yet. So it requires an environment that is entirely software-defined. If the infrastructure is controlled by standard APIs, the AI can autonomously auto-scale resources during a traffic spike, self-heal degraded systems by terminating failing containers, and provision complex testing environments instantly.
And variable 3, the crucial link, is unified telemetry.
This is the data engine we just explored. Unified telemetry provides the clean, correlated, historically accurate training corpus that advanced AI models require. It is literally the sensory input for the AI. With standardized telemetry, the agents can analyze thousands of historical deployments, recognize the subtle metric anomalies that precede a catastrophic failure, and execute autonomous remediation before a human even realizes something is wrong.
That is mind-blowing. When you synthesize those 3 variables, standardized tooling, cloud-native infrastructure, and unified telemetry, the result is the launchpad for NoOps. The entire organization is essentially terraforming its operational culture to cultivate an ecosystem where AI can survive and thrive.
Terraforming is the precise terminology. It is a complete environmental and psychological overhaul. And that brings us to the most difficult, highest friction component of this entire strategic framework.
The software is the easy part. The massive roadblock is the human beings. It is incredibly easy to sit in a boardroom, draw beautiful diagrams of a golden pipeline, and talk about AI taking the wheel. But taking hundreds or thousands of experienced software engineers, people who have spent years customizing their own bespoke, hyper-specific workflows, and forcing them to abandon their autonomy to use a centralized platform is a recipe for mutiny.
Oh, engineers hate being told what tools to use.
Exactly. How does enterprise leadership execute this transition without triggering a mass exodus of their most talented senior engineers?
That psychological challenge is the focus of Section 6, making the shift. If leadership attempts a blunt authoritarian rollout, sending a company-wide email stating that all legacy tools are banned effective Monday, they will encounter paralyzing resistance and shadow IT workarounds.
People will just build their own secret tools.
Exactly. So the framework introduces a specialized change management model designed specifically to handle the egos and friction of migrating engineering teams.
The framework contrasts traditional corporate change management with a custom model called ADAIR, a D-A-I-R. It stands for ADAIR for AI DevOps. And the psychology behind these 5 steps is fascinating. The first A is awareness.
The explicit directive here is to stop forcing tools through mandates. Instead, the platform team must generate awareness through undeniable proof of value. The framework advises running live, internal demonstrations highlighting the reduction in manual toil.
Show, don't tell.
Exactly. You bring a skeptical development team into a room and physically show them, watch this pipeline run an automated security sweep, deploy the infrastructure, and push the code in 4 minutes, a process that currently takes your team 3 days of manual configuration. You have to empirically prove the new way is superior.
You rely on the engineer's natural desire for efficiency. The D stands for desire.
Awareness proves the tool works, but desire makes them actually want to use it. You achieve this by aggressively linking the platform's benefits directly to the developer's personal pain points.
You highlight the selfish benefits.
Yes. You demonstrate how migrating to the paved road means they get to delete thousands of lines of miserable, fragile configuration code they hate maintaining. You show them that their code compiles 30% faster. You make adopting the standard path the absolute easiest, least stressful way for them to complete their daily tasks.
The second A is alignment.
Once you have buy-in, you establish the boundaries. This involves mapping out the new architectural standards and firmly installing the guardrails. The framework provides examples like enforcing a mandatory suite of IDE extensions or requiring that all new microservices include specific OpenTelemetry tracking tags before they are allowed to deploy. The teams align their daily workflows with the overarching platform architecture.
Okay, and then the I is iterate.
A massive enterprise cannot flip a switch overnight. The framework advises rolling the platform out in carefully managed sprints, starting with a pilot squad. You identify a small, highly capable, enthusiastic team, transition them fully onto the paved road, and closely monitor the friction points. You iron out the inevitable bugs in the platform, and then you use that pilot squad success metrics as internal marketing to convince the more stubborn legacy teams.
Finally, the RSS is reinforce.
Technical habits have incredible inertia. Without reinforcement, teams will slowly slide back into building custom scripts and tool sprawl. Reinforcement involves gamifying the adoption metrics on public dashboards. And crucially, it involves establishing a culture of blameless postmortems.
Blameless postmortems.
Yeah. When a deployment on the new platform inevitably fails, leadership cannot point fingers at individuals. They must focus on repairing the systemic flaw in the pipeline. And you continuously display those unified DORA metrics, velocity, quality, cost, to prove to the entire organization that the pain of the transition is yielding massive results.
That ADARE model covers the psychological roadmap, but the framework backs it up with a very rigid chronological timeline for execution. It maps out a 24-week rollout, 6 months to completely rip out the legacy infrastructure and terraform the culture. It's an aggressive timeline, and I want to walk through the 5 phases to look at where the actual friction happens during this half-year migration.
Phase 0 covers weeks 0 through 2. This is purely architecture and proof of concept. The platform team isn't migrating any live products yet. They are just mapping the existing chaotic state, designing the golden pipeline architecture, and spinning up a safe sandbox environment to mathematically prove that the end-to-end automated flow functions as designed.
Right. Then the real disruption begins in phase 1, weeks 3 to 6. IDE and Git standardization. This sounds simple on paper, but standardizing a source code management system across an enterprise usually uncovers deep philosophical divides, like the massive arguments over whether to use a monolithic repository for all code or a polyrepo structure.
Oh, it is often highly contentious. People get very passionate. But the platform team forces the entire organization onto a single source control system and mandates the standardized VS Code workspace. They begin actively deprecating the legacy, fragmented editors, and custom environments. They're laying the absolute base layer of the golden pipeline.
Phase 2 covers weeks 7 to 10, CI/CD pipelines. This is where I imagine the technical debt really rears its head.
Oh yeah, this is the heavy lifting phase.
Yeah.
The teams must take thousands of highly customized, brittle, undocumented deployment scripts running on legacy tools and somehow translate that logic into the standardized, declarative YAML pipelines of the new platform. Simultaneously, they begin actively decommissioning the old pet-like virtual machines and migrating workloads onto the cloud-native ephemeral cattle architecture.
Phase 3 is weeks 11 to 14, shift left security.
By this phase, the pipeline is flowing, so you activate those automated gates we discussed. The organization turns on the secret push protection locally and makes the CodeQL static analysis a non-negotiable blocking requirement for every single code merge. The friction point here is always alert fatigue. The new scanners will inevitably surface thousands of pre-existing vulnerabilities that were previously ignored, and teams have to triage them without halting all feature development.
Phase 4, weeks 15 to 18, is telemetry consolidation. This is where the data engine comes online.
To achieve this, without forcing developers to rewrite their entire applications, the platform team deploys sidecars.
Sidecars.
Yeah, these are essentially small independent proxy agents attached to every single container that intercept and log all network traffic and metrics automatically. They backfill the historical logs into the new unified data lake, and finally they sunset the expensive, disconnected legacy monitoring dashboards.
And the final stretch, phase 5, weeks 19 to 24. Org-wide rollout. The paved road is fully constructed and optimized. The remaining stubborn legacy products are forcibly migrated, the policy as code compliance guardrails are locked into place, and the transition is technically complete.
It requires immense discipline to execute, but the framework doesn't rely on hope. It is anchored to hard contractual metrics. The document lists the explicit ROI targets promised to executive leadership to justify the multi-million-dollar investment required to build this platform.
And those targets are incredibly aggressive. For velocity, the framework dictates a 30% reduction in lead time for change by week 12. That means exactly halfway through this chaotic migration, the platform team guarantees the code will move from a developer's laptop to live production 30% faster than the legacy system.
For visibility, they commit to greater than or equal to 95% telemetry coverage. That mandates that 95% of all corporate logs, metrics, and application traces are fully integrated into the single open telemetry platform, essentially eliminating operational blind spots.
For simplicity, they target a massive reduction in the tool tax. The explicit goal is dropping from 22 fragmented legacy DevOps tools down to just 7 core, fully integrated standardized platforms.
And finally, the metric that actually secures the funding: cost efficiency. By eliminating the licensing, maintenance, and infrastructure costs associated with those 15 redundant tools, they guarantee an annual baseline savings of greater than $250,000. It is a masterful blueprint that attacks the technical debt, the human psychology, and the financial bottom line all simultaneously.
Which brings us to the ultimate destination of this deep dive. The final slide in Roman Varel's presentation features a striking visual, an illustration of a human hand passing a glowing baton to a robotic hand. The text simply reads, "The destination is autonomy."
That image summarizes the entire multi-decade evolution. Building the paved road, forcing standardization, adopting cloud-native cattle, and enduring the grueling 24-week migration, none of these are the final goals. They are merely the necessary removal of systemic drag. They provide the stable, predictable, data-rich environment required to cross the threshold into the next era.
The text concludes with a really profound statement. It says, "A unified pipeline is just the beginning. The foundation is laid for a NoOps future where AI agents manage the operations and humans focus on the innovation. End of part one. The paved road is ready."
It reframes the entire purpose of the engineering organization. The AI agents are rapidly maturing. When they are finally deployed into these enterprise systems, they will not find the chaotic, tangled mess of the grassroots era, which, as we establish, would cause them to fail.
Right.
Thanks to platform engineering, they will find a highly structured, strictly governed, telemetrically perfect environment where they can safely absorb the burdens of auto-scaling infrastructure, executing complex deployments, and autonomously healing broken systems.
And this matters deeply to you, the listener, regardless of your specific role in the tech industry, because it represents a foundational shift in human labor. The promise of this new ops future is a world where human engineers no longer have to function as firefighters. We can eliminate the reality of waking up at 3 a.m. to restart a crashed database or spending 3 days manually resolving a deployment conflict. We can hand the heavy operational machinery over to the AI, allowing human beings to return to what we actually excel at: strategic creativity, architecture, and pure innovation.
The engine room we discussed at the beginning will, for all intents and purposes, just run and maintain itself.
Think back to that seamless experience on your couch, tapping update on your phone and watching it execute flawlessly in seconds. What we've explored today is the massive industrial effort to take that exact level of automated perfection and apply it to the intensely complex systems that make the software possible in the first place. The industry is paving the road specifically so the AI can drive.
It is a staggering evolution from developers manually throwing code over a wall to an operations team in a freezing physical data center.
It is, but tracing this trajectory leaves me with one final lingering thought. It's a question that isn't answered in the source material, but it's the reality we're all rapidly accelerating toward. If we successfully build this new ops future, if autonomous AI agents eventually take over all the operational logistics, if they run the integration tests, if they enforce the complex security gates, and if they start utilizing the unified telemetry to automatically write and deploy the bug fixes themselves, what exactly will the role of a human developer look like 10 years from now? Will we still be coders sitting at keyboards typing syntax? Or will we simply become high-level conductors, standing on a podium, guiding the creative direction of an AI orchestra?
It's a wild thing to think about.
It really is. Thank you for taking this deep dive into the source material with us. Keep questioning the systems around you, and we'll catch you on the next deep dive.